Okay, I left my flash drive at home, so I'm just going to use a whiteboard today, which is kind of something I've been wanting to try anyway, so we'll see how this works. You have the problems in front of you. I'm going to practice for exam 3, and the first page, actually the first 2 pages, are matching, and there are 10 matching on each one. So this is page 1. And the first problem says, is the percentage. So when you see the word percentage, that should automatically clue you into the word proportion. Which means we're already down to either option D or option E. So now we just need to know if there are 2 groups or 1. It says, is the percentage closed on 4th of July higher than the percentage closed on Memorial Day? That's 2. So we will go to option E, the 2 proportion z-test. G, you see average. So as soon as you see average, that should clue you into we have a problem dealing with means. And let's say, in a sense, options A, B, and C, and also G all deal with means. Usually B will say something more about matched pairs. Certainly if you see mean, it's going to be one of those 4, A, B, C, or G. So we need to know how many groups. Does average performance differ for different shifts? And there are 3 groups there. So with 3 groups, we have an analysis of variance. Number 3 says, is there a linear relationship? You can skip that one for now. We haven't covered it yet. It's on the homework for the next week. I'll go ahead and tell you by the final exam, there's going to be an H on here that's going to be like linear regression t-test. And if you see the word linear, and that's the one it's going to be. So we'll skip that one for now. 4, will the light bulb last for more than 500 hours on average? So again, we have average. That means we're talking about mean. And if we're talking about mean and there's 1 group, that's A. 5, is there a relationship? If you see that, is there a relationship? Most likely, you're going to have a chi-square test. And what we're looking for now is 2 qualitative variables, one of which is multinomial, or one or more of which. So we have here which of 4 local radio stations. So that could be station A, B, C, or D. That's qualitative. And the highest degree the individual has earned. And that's just put into the categories high school, associate degree, bachelor's, master's, and doctoral. So that is a chi-square test. It has 2 multinomial qualitative variables. 6, on average, so now we know we're on A, B, C, or G. And it says 50 locations were studied before policemen were assigned to patrol the locations, and after. Before, after is one of the hallmarks of a matched pair t-test, or one of the prototypical examples of a matched pairs t-test. You look at these 50 locations, get the number of crimes committed, then you put the patrols in there, and then after that you go back to the same 50 locations and calculate means. Okay, so 7, is the cholesterol level of egg eaters higher than that of egg abstainers? 100 volunteers, 50 randomly selected, while the others were made to eat at least 2 eggs a day. The cholesterol level. So we have here 2 groups, 50 assigned to one group and 50 to another. So we need to decide is whether we're talking about means or proportions. Well, cholesterol level is something that you measure on a quantitative scale. And so when you have a quantitative scale, you're talking about proportions. I'm sorry, when you have a quantitative scale, you're talking about means. Thought about that right in my head, it just came out wrong. Quantitative variable, talking about means, and there are 2 groups, so that is a 2-sample t-test. 8, have over half inherited the business from their parents. half is just a percentage. It's like the same thing as saying have over 50%. So it's a percent, and there is just one sample, so that's going to be option D. 9, is it more likely that a startup will last for at least 1 year when it's part of a larger chain compared to, so they'll either last or they won't. So that's qualitative variable, 2 categories, and then compared or not. So that's really 2 proportions. The proportion that lasts for a year when it's with a chain, and the proportion that lasts for a year if it's not a chain. So that's option E. And to people in, so we have average income and 2 groups, those living in houses and those living in condos. So that'll be option C. Most of these problems, I think, are pretty straightforward. If you see a zero relationship, it's chi-square. If you see means, you're going to be A, B, C, or G. 1 sample, it'll be A. 2 separate samples, C. 3 or more separate samples, G. And it has a matched pairs, which typically would be before and after or pre-post test. It'll be B. The other time that you can have one of those, like 7, it doesn't tell you whether you have means or proportions. You kind of have to know about the variable cholesterol level. And maybe that might have been a bad choice. I'm not sure. You guys are, when you get older, you'll understand cholesterol level a little bit better. But it is a quantitative variable, and you would compute averages for those. And the other one that I thought might be a little, if they say proportions or percentages, you're in D or E. So if it doesn't say percentage, proportion, mean, average, you have to look at the characteristics of the variable. So in 9, we have a qualitative variable, lasts for longer than a year or not, and then 2 groups. So all of them except for 7 and 9 should have been very straightforward. 7 and 9, you have to look at whether or not you have a qualitative or a quantitative variable. Okay, looking on at page 2. Okay, so is there a relationship? You should already be thinking chi-square. Gender, qualitative variable, type of movie, comedy, drama, romance, science fiction. That has more than 2 categories. So that is, in fact, a chi-square test. Is the average, so now we're looking at A, B, C, or G again. Now we have Russellville residents and Dardanelle residents. That's 2 groups, 2 separate groups. That's C. F, is there a relationship? Here we go again. 2 qualitative variables, whether or not support the proposed financial regulations, and then political affiliation. So that is a chi-square test, F. I must have written this a couple of years ago when that was pretty big news. D, do more than half, that's like saying do more than 50%. Have they bought the Arkansas State Lottery ticket? That is percentage or proportion, 50%, and there's 1 group, so that's option D. 5, do more than 10% of Russellville homes have, so there's just 1 sample there. That's also, they either have them or they don't. B, we've got these attitudes, and they're measured before and after. That should be enough of a clue before and after that's a matched pairs. 7, average number of books read by, there's just 1 group here, Russellville residents, so that's A. 8, another one on average, and now the average lottery tickets purchased by Russellville residents, again, just 1 group, that's A. Which of 3 methods for throwing a frisbee is best in terms of average distance? So we have average, 3 groups, that is G, analysis of variance. And then 10, percentage, so we know we're going to be in D or E. I suppose you could word an F, word chi-square as percentage, but that's really another context than that we've talked about. But anyway, is the percentage who bought the ticket different from the percentage in Dardanelle. So 2 groups, that is a two sample proportion z-test. You can expect to have at least 1 page of these on exam 3, and 1 or 2 pages, or maybe I think sometimes I can fit 15 or 16 of these on the first page, and you can expect that on the final exam. Okay. Try it this way. More than one way to get things done, I guess. So we'll try this. I think I had the mark already up. So now looking at number 1, we have a random sample of 200 citizens living in the northern United States. Of those, 140 support a roads program, and in the south, 110 support. And if you can't tell already, we have 2 qualitative variables, and we're going to have proportions. If you went on down to option B, you can see it says a confidence interval for the difference between 2 population proportions. So if you were looking back on page 1, difference between proportions, this is a 2 proportion z-test, or a 2 sample proportion z-test. Are the sample sizes large enough? Remember in the tests for qualitative variables, whether it's proportions or chi-square, that we're looking for the number in each category to be 5 or more. So in the first group there in the northern, we have 140 who support. And since the total sample is 200, that means that 60 did not support. And then in the south, we had 110 support. And that was also out of sample of 200, so that means 90 did not. All of those are greater than 5. That means that the sampling distribution of p hat A minus p hat B is in fact a bell curve, and that means it is large enough to use the z-table and to do statistical inference in this problem. So question B says, use your calculator to construct a 95% confidence interval for the difference between the 2 proportions. So if you go on your calculator and do stat tests and then let me look. I think it says 2 prop z interval. Make sure that if you're doing the interval, if you do the test, you can put the data in there, and then you'll just have to go back and do the interval. But if stat tests 2 proportion, yes, it says 2 dash prop z interval. That's what it looks like on mine. Anyway, if you'll select that, then all you have to do is put in the numbers from our problem here, where x1, which is the same as xb, is 140, then n1 is 200, and then go on down and select 95% for your interval, and then calculate, and you should get 0.05626. And then the upper, that's the lower limit. This is 0.05. I think I said that right and wrote it wrong. 0.05626. And then 0.24374. So that would be what you have on your confidence interval. C, based on that interval, can we conclude there's a difference? And the answer is yes. You can just say the interval doesn't include zero or entire interval is greater than 0. If you just said it didn't include 0, that would also be correct in this problem. Part D says write the formula that you would have used to calculate that. Of course, we just used the calculator, but I want to see now that you could, if need be, write the formula for this. It is the statistic, p hat A minus p hat B. The same statistic that I put up here, the difference between sample proportions, since we have 2 here. Proportions are always z-values. And then for the confidence interval, p hat A, q hat A, NA, plus p hat B, q hat B over NB. So we'll need to get those sample proportions. In group A, we would have had 140 over 200, which is 0.7. And p hat B would be 110 out of 200. I hope the board isn't wobbling on you guys like it is on me. Well, anyway, p hat A minus p hat B. If you wanted to just put 0.15 here, I would allow that. In fact, I would almost prefer it, just the 0.7 minus the 0.55. But I'm going to put it all in here so you can maybe see it if you're having trouble with this. The difference between the two sample proportions, plus or minus. And we did a 95% confidence interval, so that's going to be 1.96. All right, p hat is 0.7. All right, p hat is the proportion that said yes. Q hat is the proportion that said no. Those have to add to 1. I guess you can look at it, if there were maybes in set, you could say the proportion that said yes and the proportion that did not say yes. This is a binomial variable. And then we had 200. And then in the second group we had 0.55. 1 minus that, which is 0.45. And that's all it asked for. Write the formula and put the numbers into it. Of course, we've already solved it up here, and if you want to put that formula in and check that you can do that, you ought to get something that's pretty close to what I have up there. You probably, well, you may get exactly. I'm not sure how much rounding error. It depends on how you put it in. And so E says, now suppose that we were doing a hypothesis test for the difference between, write the form that you would use to calculate the test statistic and then put the numbers into that. So it would be Z test. It's equal to the statistic. Again, that's p hat A minus p hat B. Minus the hypothesized parameter. In this case, that's always going to be 0. That's just a hat above that PB there. Marker's not exactly. This part, the hypothesized proportion, I like to write it just for, I guess, theoretical reasons, but because I want to emphasize statistic minus hypothesized parameter, but it will always be 0. And divide that by the square root of P bar Q bar 1 over NA plus 1 over NB. So, on the top, P hat A minus P hat B, that's 0.15 or 0.7 minus 0.55. And on the bottom, we're going to have the square root of P bar. P bar is the weighted average for the whole group. So we had a total sample size of 400, 200 in each group. And we had a total number of yeses of 250. That's just 140 plus 140 plus 110. That's 250. And that all comes out to be 0.625. So here we'll have 0.625. 1 minus that, 0.375. One over NA, which will be 1 over 200. And the same thing for B, 1 divided by 200. Okay, that's number 1. Okay, so we'll look at number 2 now. We have 2 qualitative variables here, one of which is multinomial, so that's going to be a chi-square test. And HO, let me do HOR first. There is a relationship between residence, which is Russellville or Dardanelle, and type of car one drives. HO would be no, there isn't, or just unrelated. No relationship. So let me make a big table here. Yeah, let me make it bigger actually. Oh well, really like to have this even bigger than it is. I think I'm going to try. Let's see if I can. To make this even narrower here. I'm just writing down the numbers in the problem as they are given. These are the observed values. That's a 26. 12, 23, and 13. And now what I'm going to do is add up all the rows and the columns. And when I did that, I had 200 and 200. which that's nice. We're going to have a 50-50 split across columns. So here we have 48, 78, 38, and 36. So since we have a 50-50 split in the columns, here we have an expected value of 24 and an expected value of 24. So of that 48, half in each. And then I'm going to go ahead and get all of these. Expected value here is 39. That's half of the 78. Half of the 36. Now I'll have mine come out to be 50-50 splits, or some other split, 1/3, 1/3, 1/3, or 25%, 25%, 25%, 25%, most likely a 50-50 like this. That's just because I think it would be easier for you to understand what an expected value is. But I hasten to add that we could have gotten this 24, any other number on here, by taking the row total times the column total by the grand total. So we would have had the row total in this one would have been 48. The column total is 200. And then the overall total is 400. And of course, that'll come out to 24. Okay, moving back over here, we're going to reject HO if chi-square test is greater than, it's going to be 7.82, and that's off of the chi-square table with 3 degrees of freedom in alpha 05. It's 3 degrees of freedom. If you took one row and one column off here, there'd be 3 left. Or if you just want to do row minus 1, this is just number of rows minus 1, number of columns minus 1. There are 4 rows minus 1 times 2 columns minus 1. And of course, that comes out to be 3 degrees of freedom. So now what we'll do is we'll calculate the chi-square test, and the chi-square test is equal to the sum of the observed minus expected squared divided by expected. So for each cell, we'll get the observed value minus the expected value, square that, then divide it by the expected value. So here we'll have the observed value, 20, minus the expected value, 24. Square that and divide by 24. And you should get 0.67 for that. I'm going to circle that just to make it easier to see when I go to do my adding. Here we'll have 28 minus 24 squared divided by 24, and that's also equal to 0.67. And this one will have 31, the observed, minus the expected of 39. Square that, divide by 39, and that's equal to 1.64. Then we'll have the observed value, 47, minus the expected of 39. Square that and divide by 39. We'll get 1.64. And really, in a 50-50 split, we're going to get a 50-50. We're going to get the same rows and numbers in each row. So on the next one here, now that won't always be the case, but it will be with a 50-50 split. So 26 minus 19 squared divided by 19 is equal to 2.58. And I'm just going to tell you over here, as I said a second ago, that's going to be 2.58. And then here we've got 23 minus 18 squared divided by 18. And that's equal to 1.39. And this one will also be 1.39. So the chi-square test will be the sum of all of those O minus E squareds over E. So 0.67 plus 0.67 plus 1.64 plus 1.64 plus 2.58 plus 2.58, sorry, made the mistake of putting my hand on the board. That's why we got those stray marks there. My bad. The board's kind of shaking on me a little bit, so I just thought I'd try and hold it still, but maybe not. 1.39 plus 1.39, and all of that comes out to be about 12.56, which is, of course, greater than 7.82. So we reject HO. I'm going to write that in just reject HO and conclude that there is a relationship between residents and the type of car that they drive. It looks like, if I were to make some overall statement about this, that in Dardanelle they seem to be driving General Motors and Ford, that is more American cars, or cars made by American companies, or companies that are housed here. I guess Toyotas are probably made here as well, but the company is not an American company. And that seems to be more a Russellville thing. So now on to number 3. Do more than half of ATU residents consider themselves sports fans? Simple random sample of 72 anyway, identified themselves as sport fans. And that is a qualitative variable. Do more than half, that's like a percentage. And so X, I think I'm going to try and switch to back to that thicker. X is equal to 72, N is equal to 100. They either consider themselves sports fans or not, so all we can get is the sample proportion. That's 72 out of 100. If you want to write X over N, you may. That's 0.6. So is the sample size large enough? In part A, we just need the numbers of yeses and number of noes. 72, that's greater than 5. And then sorry about that. N was, I usually use 100, but in this case, I used 120. Probably were wondering how I got 72 divided by 100 and got 0.6. Sorry about that. And then 120 minus 72, which is 48. Those are both greater than 5. So that means that the sampling distribution of p hat is a bell curve, and then we can have statistical inference. Okay, so B, for HR, we want to know, is it more than half? So is P greater than 0.5? And HO P equal to 0.5. So now it asks to do the p-value approach and draw the sampling distribution. This is part C. We know, because the sample sizes were large enough, that we're going to have a bell-shaped sampling distribution for the p-hats. We know that the center of that is going to be whatever is in our HO, so 0.5, and that here we locate the specific p-hat in this sample, which is 0.6, and the area out here will be the p-value. And this is a z. All of the proportions are z's. So we can calculate, if you want to call it z or z-test, I'll go ahead and call it test because it would be a z-test. It's going to be the statistic minus the hypothesized parameter divided by the standard error, which for hypothesis testing is going to be p-h QH. Make sure you use the hypothesized and not the p-hat when you're calculating these, and then N. So we'll have 0.6 minus 0.5 divided by the square root of 0.5, 0.5. Let's see if I can get the sample size right this time. That's 120. And that all comes out to be 2.19. Well, when you have a z of 2.19, if you look in the z table, you'll have an area of 0.4857. Remember, you'll always get you'll always have, when you get X out, well, that was pretty good. When you look up an area in the z table, that's the area from the center of the distribution to the point of interest. So that's that. And then the p-value itself, the area in the tail, will be 0.5 minus that, 0.0043. And that's it for part C. For part D, it says test the hypothesis. So we're going to reject the null hypothesis if z-test. Okay, sorry about that. We're doing p-value approach. If the p-value is less than 0.05 and 0.0043 is less than 0.05, therefore we reject HO and conclude then that P is greater than 0.5. that the difference that we have here is not simply a matter of sampling error. So finally then we have our if-then statement. Remember, that's going to be if HO is true, there's a p-value chance of observing what we did observe or what we have in the tail of the distribution. Remember, the p-value always goes in the direction of the research hypothesis. It's possible if we had said less than 0.5 on this and we got 0.6 that the p-value would have been 0.9857, everything from there down. But assuming that our hypothesis at least went in the right direction, it'll be like this. So if p is equal to 0.5, then there is a very small chance, a 0.0043 chance that we would get a sample statistic of p hat in this case greater than or equal to 0.6. So moving on to number 4, this is really the same information we just had. So we have p hat is equal to 0.6, and we want to do now construct a 90% confidence interval. So that's going to be the sample statistic plus or minus a confidence coefficient, which will be z for all proportion tests, p hat q hat over n. So 0.6 plus or minus 1.645. 0.6. Now see, now there is no specific hypothesis that we have to test with a confidence interval, so we'll use the p hat. Remember, in the hypothesis testing, we used the pH, the 0.5 and 0.5. For the confidence interval, use the p hat. Yay, I got the 120 right. And that comes out to be 0.5264 to 0.6736. I encourage you to use your calculator to verify that that is in fact the right answer. That's stat test 1 prop z test, and you would plug in the 72 and the 120, tell it you have 90%, and go down and hit calculate. I encourage you to do that to make sure you can do it if that was needed on one of the exam problems. Based on that, can we conclude that there is a... Okay. On mine right now, this is going to say, can you conclude that the population proportion is greater than 0.5? So is it p greater than 0.5? And so the answer would be yes. The entire interval, I really would like for you to write entire, is greater than 0.5. Okay, and finally, well, I guess not finally, there's 2 more problems here, actually. So looking at number 5, we want to assess the mean. And a survey 10 years ago had a sample mean of 1,400 and a sample standard deviation of 1,000. But we want to get a confidence interval now. And when we do that, we're going to have x bar, which is going to be a new x bar. It's not going to be the 1,400, plus or minus, and it's going to be z or t. This is a problem calculating sample size, so we're going to use z. You actually can use s, but there's an iterative process, and this will get us close enough. Or to get the idea out there, the standard deviation divided by the square root of n. This is the margin of error. And so we want a margin of error of 100. We want 95% confidence. That's 1.96. And the best estimate we have of standard deviation is this 1,000. And technically, I won't hold you to it, and I don't always hold myself to it. We should have a hat over there because it's an estimated population proportion. Not all books put there, but technically it should have that, the square root of n. So now n is going to equal 1.96 times 1,000. It takes you more steps to get this than use them. Divided by 100. Take all of that. Try and take all of it. And square it. And when I did that, I had 384.16. You should always round these up. That's the minimum, and you can't. The 384.16 is the minimum, but you have to have a whole number, and 384 wouldn't meet that, so always go up. 385 or more. Just like that, but greater than or equal to 385 would be the sample size you would want. Let me hasten to add that had that number come out to be that sample size, let's say it had come out to be 36. If that were true, the 36, as the 385 in this problem, would satisfy the desired margin of error, but we would still have to look out, if it were 36, for outliers and extreme values. Okay. So we'll carry on to number 6 now. So now we want to estimate, we want to have a confidence interval for the population proportion that own one or more iPads. And we want to know the sample size, and we want a margin of error of 2%, which is 0.02 in proportions. And so when we get around to doing that confidence interval for the population proportion, it's going to be p hat, the sample statistic, plus or minus z times the square root of p hat q hat over n. And again, this is the margin of error. So margin of error, which is our 0.02, is equal to z. We want a 95% confidence. So that's 1.96 times the square root of, all right, I'll put n down here. That's what we're looking for. Had there been a pilot study, and let's say that in the pilot study the sample proportion was 0.2, then we would use 0.2 and 0.8 here. When there is no pilot study, you should always use here 0.5 and 0.5, because when you have 0.25, which is the product of those at the top there, that's the highest product of P and Q that you can get. And so this is the most conservative estimate that you can have for sample size. And so N is going to equal 1.96 divided by 0.02, square that, times 0.5 times 0.5. For whatever reason, a lot of people, I guess when they're working the problem, end up squaring those again. Don't do it. And that comes out to be exactly 2401. So you should have at least 2401 in your sample. Okay.